This presentation introduces fundamental features of Element CXI's Elemental Computing Array, the ECA. This is the first of 4 presentations describing Element CXI hardware and software. This presentation on architecture focuses on fundamental comparisons with prior art and CXI innovations from a hardware perspective. The tools presentation will cover expectations as established by the reconfigurable device market in the last 25 years. The advanced features presentation will describe new features found in the ECA, which have no comparable basis in prior art. And the IDE presentation will illustrate what's necessary to meet and exceed expectations to succeed in the mature reconfigurable device market. Your presenter is Stefan Wasson, a founding member of Element CXI's engineering team, a co-founder of Morphix, a reconfigurable base station company, and a co-founder of Highgate Design, a guild of FPGA design and implementation specialists. I began implementing Xilinx FPGAs in 1987 for up-to-date technologies, which was later bought by Chipson Technologies. At Highgate, I implemented over 350 FPGA designs and evaluated architectures for clients such as Concurrent, Cadence, Vantas, and Xilinx. That reputation led to founding Morphix, where we raised $65 million in funding for 120 employees. And that led to the opportunity to help co-found Element. In all, a 25-year focus in reconfigurable logic, architecture, and tools design. The CXI material in this presentation is covered by the following patents. The purpose of this presentation is to illustrate the primary distinctions between the Element ECA architecture and prior art. Understanding what's old and what's new sets the stage for the next presentation on tools. As we shall see, the primary distinctions between the ECA and prior art FPGAs are compute block granularity, interconnect schema, multi-context operation, and configurability. There are more incomparable distinctions, but as previously mentioned, these will be covered in the advanced features presentation. This presentation is organized into the following sections: playing field, who's in, who's out, where do we fit, resources, composition, granularity, and arrangement, interconnect, granularity, structure, type, I/O, and scaling, timing, repeatability, determinism, and closure, configuration, logic, methods, and latencies, multi-context methods, and summary. CXI is competing in an ostensibly crowded field. The playing field for reconfigurable device arrays can be divided between arrays of bit and bus granularity. The bit granularity devices can be further subdivided by compute block granularities between gate or LUT arrays, while the bus granular devices can be subdivided by compute block granularities approximating operator, task, or DSP and micro-P arrays. The bit granular gate LUT arrays belie a physical hardware implementation use model, while the bus granular arrays infer a software program perspective. Plessey is an example of a true sea of gates, while Xilinx and Altera are the exemplars of the most crowded category of LUT arrays. The second most crowded category is the DSP micro-P array-based segment. Whereas TI is the dominant DSP player, insofar as arrays are concerned, there's no clear winner here. Quicksilver is, or was, an example of a task-based architecture, while CXI is an operator-based architecture. Some companies, like ASI and M2000, straddle several of these segments. Over the past decade, dozens of architectures have come and gone, and over half of those shown on this playing field have either shut down or been acquired. The comparisons in this presentation will focus on our neighbors in the adjacent market segments, the LUT and task-based architectures. And now for our first set of comparisons: device resources, composition, granularity, and arrangement. In the market segment with device granularity below the ECA, prior LUT-based ART, like Xilinx, is built around small, function-centric configurable logic blocks, featuring a small number of bit-sized inputs, outputs, LUTs, and flops. For example, a block with 4 1-bit inputs, 2 1-bit outputs, a pair of 4-input, 1-output LUTs, a pair of registers, and a pair of bypass muxes for selecting either the combinatorial or sequential output. This granularity of block supports simple Boolean functions like invert, AND, OR, XOR, and more complex logical equations of 4 1-bit variables. This composition has been the standard archetype for 2.5 decades. In the market segment just above the ECA are task granularity prior art architectures like Quicksilver, consisting of very coarse, task-centric programmable nodes featuring, for example, 32-bit I/O pipes isolating the programmable node from the rest of the array, a 16 kilobyte memory to store instructions of input, interim, and output data, a very coarse-grained execution unit with a plethora of multipliers, ALUs, accumulators, or a RISC core with RAM, a microprocessor for task management, and a DMA controller for moving data stored in and out of the node memory. This coarse granular node supports such tasks as FIR filters, Viterbi decoders, and FFTs. The ECA architecture is based on medium granularity operator-centric configurable elements. For example, 4 18-bit inputs and 2 18-bit outputs implemented as 16-word register files with extended capabilities like merging and mapping, a medium-grained execution unit composed of, for example, adders, multipliers, and accumulators, a small sequential processor with 32-word register files, or a memory controller with programmable address generators. Not a micro-P, but an FSM containing an arbiter to negotiate execution as a function of I/O readiness, and config registers to define element behavior. This granularity of node supports such operations as add, subtract, and multiply. The structure of prior art LUT-based FPGAs is a flat 2D array of homogeneous programmable function blocks interconnected by bit granular segmented interconnect. It took about 10 years to introduce a second block type, memory, another 5 years or so to introduce math or multiplier or DSP blocks, and a few years more to embed some kind of micro-P. The result is a 2D array punctured by disparately sized blocks with a variety of interfaces. The structure of the CXI ECA is an array of interconnected clusters subdivided into interconnected zones. Each zone is a collection of interconnected elements. An element is a common wrapper around a collection of compute kernels, each implementing a different instruction set. Compute kernels include programmable data flow operators, memory and memory controllers, and sequential processors. Wrappers enforce a standard interface and hide the compute kernel complexity. The instruction set of data flow operators includes arithmetics, multiplication, shifting, bit manipulation, and many more. The memory set includes FIFO, block, burst, and address manipulation instructions. And the processor set includes all the general load, store, move, I/O, and interrupt instructions, as well as instructions specialized for managing and exploiting the ECA array. Device interconnect, granularity, structure, type, I/O, and scaling. The interconnect of prior art LUT-based FPGAs consists of 2D orthogonal, vertical, and horizontal interconnect segmented in various full-length, half-length, quad-length, and other shorter length lines, all of bit width granularity and none with any embedded protocol logic. All of these segmented lines are interconnected with programmable interconnect points, or PIPs. Every PIP has a bit in the configuration bit stream representing the on-off value for the interconnect switch. The standard FPGA interconnect also has a plethora of so-called magic boxes embedded throughout the interconnect array and offering a multiplicity of lane change options. These lanes are heavily connected to the interconnect array by pip grids. The function blocks are nested within the interconnect array with inputs and outputs both connected to the interconnect grid. There are special vertical lines, such as carry chains, also connected to the interconnect array. The CXI ECA has two distinct bus granular interconnect resources. The first is a 2D bus granular data flow interconnect that transports data between adjacent clusters, and the second is a bus granular hierarchical message interconnect in the z-axis. ECA data flow is conveyed through FIFO-like queues. These are data-driven interconnect designed specifically for data transport. There is no need for the user to design control signals for this resource. Clusters are interconnected with a collection of unidirectional queues. Now recall that an ECA cluster is a collection of zones. Adjacent zones are also interconnected with FIFO-like queues. Zones are also diagonally interconnected with queues. Zooming in on a zone, each zone is a collection of elements, and elements are fully interconnected, every data source to every data destination. Clusters are additionally interconnected by the second type of interconnect, which is the hierarchical interconnect in the z-axis. This bus granular interconnect is message-based for writing and reading configuration data. Every cluster set, called a supercluster, has a transport switch that interconnects the superclusters. These switches, in turn, are interconnected with each other. This resource may also be used to transport application data in and out of any cluster. In prior art FPGAs, I/O is all bitwise, universally accessible from anywhere within the array. It's not quite as simple as this, since these I/O actually incorporate programmable logic and support dozens of I/O standards. Because the ECA has two interconnect resources, it has two port types, one for the 2D, bus granular, data-driven, data flow interconnect, and another for the third dimension, bus granular, message-driven, configuration and application data. Both of these are unidirectional ports. The data flow ports connect directly to the clusters, while the message ports connect to the supercluster transport nodes. The data flow ports also use FIFO-like queues to support their streaming data protocol. Tiling. What is it, and why is it important? Tiling is the replication of device regions to make larger arrays. It's important because it predetermines device performance scalability. In particular, it anticipates performance degradation from linearly scaled interconnect, which is increasingly difficult to reach in the traditional center of the array, an effect known as center starvation. In traditional FPGA arrays, timing is compromised by center starvation. The typical reconfigurable device has 9 regions, here arbitrarily numbered 1 to 9. These regions contain the replicable tiles. Besides the 4 corner regions that often contain clock and control, and the 4 edge regions that contain I/O tiles, the bulk of the device is composed of the center region. The center tile is the most important, since it comprises the extensible logic tiles of configurable logic blocks. User interconnection is limited to the X and Y axis, which results in an increasing inability to reach the center blocks as resources are consumed. The larger the array, the worse the problem, because routing does not scale with increased X and Y dimensions. Hence, this tiling structure cannot assure application performance preservation with device migration. Another version of prior art tiling that adversely impacts its configuration and debug channels further subdivides the center into 4 subregions, here arbitrarily numbered 11 to 14. These regions are generically named center, top, bottom, and edge. Again, the center region is the most important, since it comprises the extensible two-dimensional logic array of center, top, bottom, and edge blocks. This exemplar illustrates that config-debug access not only constrains nodes to adjacent interconnect, but constrains them to the top and bottom column edges. As before, this results in significant increased delay as array sizes scale up. Another version of prior art tiling scales its center region of programmable nodes hierarchically. Each group of 4 nodes is connected by an interconnect node. Node groups are again interconnected by another up-level interconnect node. This center region is a 2-dimensional array of programmable nodes and a succession of interconnect nodes. All user, config, and debug connections share, that is, are constrained to the hierarchical network. This creates an I/O bottleneck at the external I/O port. ECA tiling combines locally adjacent 2-dimensional interconnect for data flow with hierarchical message flow by scaling its center region of programmable nodes in 3 dimensions. First, each group of clusters, here 4, is connected by a first-level interconnect node, the transport switch. Node groups are again interconnected by another up-level interconnect node. This center region is a 2-dimensional and hierarchical array of programmable clusters, where all edge clusters have external data flow ports, where each supercluster is connected by another interconnect node, each one of which has its own external message port, and which is connected to an up-level interconnect node that has its own collection of external message ports. As previously mentioned, all message ports may transport configuration or application data, and these ports may also be used for debug. So this tiling structure is truly extensible because it preserves performance with array scaling. To illustrate prior art interconnection, let's do a routing example. Suppose we want to connect F1 to F9. At F1, we can choose one of 2 outputs. Let's choose the top output. Then we have a choice of getting onto 3 vertical segments. Let's choose the middle segment. Then the route can go either up or down. If the route goes up, it has a multiplicity of horizontal segments from which to choose: long lines, half-length lines, local lines. If the route goes down, it has a multiplicity of lane change options through a magic box. Let's suppose the route continues down through the magic box, making a lane change. This choice determines the next vertical segment of the traverse. Now, the segment could either use a nearby function box as a pass-through, or it could continue through the next magic box, where it again has new lane change options. Let's suppose the route continues through the magic box, making a corner turn lane change, onto the next magic box with another set of lane change options. Again, let the route take another corner turn onto another vertical, where, if it's smart, it'll use one of 4 inputs to the final function box F9. Let's suppose the router is smart and chooses the first input to F9, and thus this single-bit route with its myriad choices is complete, for now. Every single one of these route segment choices is reflected by edits to the stream of configuration bits. For just this connection alone, over this tiny distance, in this tiny sample array, where function blocks have 2 outputs to 3 vertical channels with 7 connection options, and where magic boxes offer 7 lane change options to another vertical with 5 connection options, and 2 more 7-option lane changers, to 3 vertical channels, and finally to 1 of 4 inputs, there are nearly 10 to the 6th routing choices, and all this for just one 1-bit wire. Furthermore, final timing actually remains unknown until every last route is laid down. And today's FPGAs have far more routing resources and therefore decisions to make than this. By contrast, the ECA does not route connections like an FPGA. Routing is a static connectivity process. Instead, the ECA binds destinations to sources. Binding is a dynamic process. Recall the ECA structure, an array of interconnected clusters with interconnected zones comprising each cluster and interconnected elements comprising each zone. Any element can connect to any other element by configuring its input source register to selectively subscribe to the input of its choice. Note, the binding process need only be applied to the data stream interconnect, not the message interconnect. Every destination input has a mux selector with inputs from every zone source. These are 18-bit data flow buses, not single-bit wires. Source selection is determined by that input register's configuration word, source field. Thus, every destination in a zone can be connected to any source in that zone, any zone element, or any zone queue. Once a source is selected, Q0 for example, the destination additionally selects which source context to listen to. Context selection is determined by comparing the value on the input context control lines to the config register context field. In this way, a destination may subscribe to any specific source context. We'll get to the multi-context feature of the ECA a little later in this presentation. There are subscriber registers for every destination input. The memory-mapped configuration bus can access any of these destination registers. The entire configuration register map is accessible at any time. In other words, all destination binding is dynamic and can be altered anytime during operation. Device timing, repeatability, determinism, and closure. In an FPGA, there is no predicting what route you'll get, or how long its delay will be. But in an ECA, in a zone, the interconnect between every source and destination is the same. And therefore, this unit delay interconnect is deterministic before binding. Because prior art uses bit-granular, non-predeterministic resources, its timing is non-predeterministic, that is, cannot be known a priori. Consider 2 signals laid down, routed, in the same configuration interval, for example, 2 bits from the same bus. From their sequential sources, flip-flops 1 and 2, signals D1 and D2 traverse to the sequential destination flops 3 and 4. For the given route interval, here T1, signal D1 has delay delta 1, and signal D2 has delay delta 2. These delays are exceedingly unlikely to be equal. Now, consider one signal routed at two different times. For the first route, in T1, from its sequential source flip-flop 1, signal D1 traverses to its sequential destination flip-flop 3 with delay delta 1. But for the second route during T2, the same signal D1 sourcing from the same flip-flop 1 traversing to the same destination flip-flop 3 is likely to have a different delay delta 2. Because FPGA routing algorithms are influenced by changing netlists, assuring predeterministic timing is a practical impossibility for both these cases. However, in the CXI ECA, because of bus granular and deterministic resources, D1 and D2 will always have the same delay. For the same reason, every time D1 is bound into the device, same source and destination, it will also have the same delay. This determinism is a huge advantage in maintaining and guaranteeing IP bandwidth, especially with reuse. Device configuration, logic, methods, and latencies. Prior art uses dedicated logic and dedicated I/O for device configuration. After configuration, this logic is unavailable for and separate from user logic. Prior to runtime, the configuration stream passes through the configuration logic to the user array, after which the application data may flow through the array. Only with the application halted may configuration data be extracted. The simple timeline of these events illustrates their non-overlapping nature. First, the user configuration is written prior to T0. The application runs until halted at T(in), and only then may configuration data be extracted. CXI ECA configuration is considerably more versatile because there is no dedicated configuration controller. It's all user logic and user I/O. Recall that the ECA has two port types, message ports and streaming data ports. Message ports can transport configuration data in or out. They can also transport application data in or out. And this can all be done coincident with streaming data. While one region is continuously streaming data, another can write or read configuration data. Or, one region can write or read configuration data of the streaming region. Or, a region that's streaming data can rewrite and read its own configuration data. Similarly, while one region is continuously streaming data, another can write and read application data. Or, one region can write and read application data to and from the streaming region. Or, a region that's streaming data can also simultaneously use its message ports to transport application data. And this can all be going on simultaneously. It's even possible and practical for the device to generate its own reconfiguration data in real time. In prior art, partial reconfiguration has been impractical. Consider two configurations through three logic columns for signal 1 to signal 2. The configuration bit stream at T1 lays in a path through function 1 and around flip-flop 1, through function 2 and through flip-flop 2, and through function 3 and around flip-flop 3. The T1 path delay is P1 plus P2. Now suppose we wish to partially reconfigure this path to bypass flip-flop 2. At T2, a new configuration stream is input, selecting the bypass mux, MX2, so the T2 path delay is P1 plus P2 minus the flip-flop 2 setup and clock to Q. This creates obvious problems on either side of flip-flop 2. During T2, flip-flop 2 may be taken out of service, but signal 1 is still active. Moreover, destinations of signal 2 are still listening. Prior art FPGAs have no mitigation logic to address these vulnerabilities. The ECA introduces two innovations to mitigate prior art partial reconfiguration problems. One low-level construct and the other high-level. The ECA is a multi-context device. Between sequential components, contexts are selected under program control. Given 8 contexts performing 8 operations at T0, suppose we want to reconfigure F4 at T1 with new function F4 prime. While context 4 is out of service, all the other contexts may continue to fire. Context 4 input data is stalled and output data is flagged as not ready. This prevents the upstream and downstream confusion inherent in FPGA architectures. Once the reconfiguration is complete at T2, the reactivated context rejoins the execution list for the remainder of the run. The high-level construct permits reconfiguration of context sets called tasks. For example, given 8 elements, each performing 8 operations, in which one context from each element belongs to the same task at T0, all task operations can be concurrently suspended at some later time T1. Contexts can then be successively reconfigured. When reconfiguration of the new operations is complete, the task is reactivated and its contexts will rejoin their execution lists for the remainder of the run. In prior art, there are 2 reconfiguration models, the linear 1D model and the coordinate 2D model. In the linear model, to access any bit, an entire bit stream must be loaded or unloaded. In modern FPGAs, this is millions of bits, requiring milliseconds of time. In the coordinate model, for a device with X columns and Y rows, to write data at ij, config data must traverse I columns and j rows. And to read ij data requires traversing x minus I columns and y minus j rows. In a large array, this method requires hundreds of hops. By contrast, the CXI ECA uses a hierarchical reconfiguration model. At the bottom are cluster nodes, arranged in superclusters, tied together at the next up level by message transport points, which are in turn tied together at the next up level. In a hierarchical structure of depth L, the time it takes to write is L hops, and to read 2L minus 1 hops. In a device with 1,000 elements, L is 2, significantly more expedient than prior art. The multi-context implementation is perhaps the most significant ECA innovation. Prior art has explored 2 kinds of multi-context implementations: time domain multiplexing, or TDM, and frequency domain multiplexing, or FDM. In TDM, between sequential components, in a given interval, a multiplicity of contexts are each allocated 1 time slot to execute their function in a round-robin fashion. One problem with this scheme is its invariance in time and slot allocation. In the FDM implementation, between sequential components, for a given interval, the multiple contexts are each allocated 1 or more time slots to execute their function. In FDM, time slot allocation is programmable. In this exemplar, the first 4 slots are assigned to context 1, the next 2 slots are assigned to context 2, and the last 2 slots are assigned to contexts 3 and 4. This has the effect of increasing the run rate for some of the selected contexts. Here, context 1 gets half the bandwidth. Context 2 gets a quarter. Context 3 gets an eighth, and context 4 gets an eighth. Like TDM, FDM context execution is fixed order. Furthermore, this program control is a priori, that is, not real-time dynamic. Another problem with this scheme is its inefficient context utilization. Note that in this exemplar, context 5 to 8 cannot even execute with this time allocation. The CXI ECA multi-context implementation is data domain multiplexed. Between sequential components, context execution is under program control and is data-driven. For a given interval, the context selector controlling function execution is data-ready dependent. So, contexts execute in data-ready order: forward, reverse, or random. Because order execution is variable, dynamic, and efficient, DDM has significant advantages over FDM and TDM. For example, in TDM, in a given interval T1, 8 functions F1 to 8, and their 8 data streams delta 1 to 8, each with data ready at time tau 0, will be able to efficiently execute in order, with each context running one slot in the interval. However, if in a second interval T2, the data streams present data later than expected, even if more data might be forthcoming, TDM context execution opportunity can dramatically suffer. Here, only context 1 can accept data, while data arrives too late for the others. Consider a third interval, T3. Again, only data streams 1 through 4 are presenting new data. Contexts 1 to 4 can consume this data, but what if these streams want to present more data, this time out of order? Their contexts will be unable to respond in this interval, again resulting in underutilization. So, overall, in these 3 intervals, while contexts 5 to 8 consumed 100% of presented data in T1, contexts 1 to 4 were underutilized. During the 24 phases of these 3 cases, work was done in 13 phases, but not the other 11. That's only an average utilization of just over 50%. Consider the exact same 3 interval scenarios for FDM. As before, in interval T1, functions 1 to 8 have data ready on streams 1 to 8 at tau 0. However, here, the T1 slots are pre-allocated, as previously shown in slide 38. The first 4 contexts are given 4, 2, 1, and 1 slots respectively. Therefore, in T1, each context can only execute once, resulting in only 4 contexts executing in only 4 slots. In interval T2, data arrives exactly when and in the amount expected, resulting in full utilization of contexts 1 to 4, precisely aligned with their pre-allocated slots. But consider T3, the out of expected order case, trying to present even more data than allocated. Only 3 of 8 slots qualify for execution, actually worse than TDM. So overall, in these 3 intervals, only 2 contexts consumed 100% of their data. 1 80%, 1 50%, and unallocated contexts 5 to 8, of course, consumed 0%. FDM phase utilization fared a little better for these 3 cases, in which work was done in 15 phases, but not the other 9, for an average utilization of 63%. Finally, let's reconsider the exact same 3 scenarios for the CXI ECA. In the first interval, T1, the 8 contexts are each presented one datum at tau 0, and each is consumed with exactly the same efficiency as TDM. All contexts fully utilized, all presented data consumed. In T2, more data arrives on streams 1 and 2 than 3 and 4. Again, all contexts are utilized with the same efficiency as FDM. And then consider T3, which neither TDM nor FDM handled well, where data arrives in reverse order and in differing quantities. But the ECA's data-driven contexts are able to respond, consuming data when and where presented, with efficiency unmatched by either TDM or FDM. For these 3 cases, the CXI ECA DDM architecture performed work in all 24 phases, 100% utilization. In summary, comparing prior art and the CXI ECA, prior art resource granularity and arrangement is varying and asymmetric, whereas ECA resource granularity and arrangement is uniform and symmetric. Prior art resource interfaces are either non-existent or vary in width and protocol. ECA resources are all wrapped in the same interface. Prior art interconnect is bit granular, variously segmented, and rectilinear. ECA interconnect is bus granular, unit delay, and hierarchical. Prior art routing suffers from center starvation. ECA binding does not. Prior art timing varies from route to route and with device scaling, and it suffers complex timing closure. The ECA has invariant, predictable, cycle-accurate timing with simple timing closure. Where prior art timing closure is impractical in the field, ECA in-field timing closure is practical. Prior art configuration is based on gate-level bit streams using dedicated logic and paths. ECA configuration is based on high-level context and task message streams through user-available logic and paths. Prior art reconfiguration latency is long, and partial reconfiguration is impractical, whereas ECA reconfiguration latency is short, and partial reconfiguration is practical, even in the field. That is, the ECA permits reconfiguration of contexts and tasks without disturbing active operations. And prior art context switching relies on inefficient TDM or FDM, whereas the ECA uses efficient DDM context switching. So, what do we conclude from all this? The element CXI ECA is less onerous than the archetypal FPGA because there are no trivial clocks, resets, or control signals that need to be wired, no dangling nets or mismatched bus widths, no setup, hold, or pulse width timing violations or race conditions, and no need to design or implement soft interface logic. Designs are also many orders of magnitude easier to place and bind. They don't need gate-level simulation or bit path timing closure, both very schedule-intensive, and it's much easier to preserve design performance targets even throughout incremental design modifications. The ECA is also more naturally suitable than an FPGA for data flow applications because of its uniform modular compute block granularity, deterministic unit delay hierarchical interconnect schema, self-timed data-driven multi-context operation, and its inherently parallel, readily partitionable multi-threaded architecture. In short, the ECA enables adaptable data path acceleration, either embedded or as a target or initiator device. Now, what tools are needed to program the ECA? That's the subject of the next presentation.